section 6.5, we're going to be talking about exponential growth. Exponential growth is basically occurs when a quantity is increased by the same factor or equal over an interval of time. So what does that mean? It's basically saying that we're doing an exponential function, but it's just increasing. So if I were to kind of give you some numbers, I start with the number 1, I go to 2, next one would be 4, the next one would be 8, and the next one would be 16, so forth, so on. Every time I'm doubling, and so that's what it's saying, is I'm multiplying by the same factor. In this case, it's multiplying by 2. This is what it means to have a growth. But more specifically, the growth factor is what we would call more than 1, and I'll show you that in just a second. So this is our basic equation that we have for exponential growth. Y equals A times 1 plus R, all raised to the t power. Now, Y represents your final amount. Your initial amount is represented by A. And this particular thing, 1 plus R, represents your growth factor. And then R specifically is your rate of growth. And then T is time. So notice this, that I have 1 plus R. So my growth factor, it doesn't matter what the rate is, my growth factor will always be more than 1, which makes sense because like a while ago, I had a growth of times 2 in this particular case. If I did a growth of times 1.1 each time, it would still be getting bigger than 1, even though it might not be this drastic a change. So that's really what a rate of growth is. It's a positive rate of growth. Therefore, we're adding it to 1 to get a growth factor that is always going to be greater than 1. All right? And then time generally is just depending on where, it's just your basic time. It could be minutes, years, or whatever, depending on whatever the problem is. So nothing too complicated on that. All right, we do have something in here that's called compound interest, and there's a bunch of jibber jabber here. I will come back to this later, but let's go ahead and look at some other information here. So in this particular problem, it says this: identify the initial amount, A, and the rate of growth of the exponential function. And it's asking me to find the rate as a percent. We'll talk about that again. And then it says evaluate the function when t is equal to 4. So basically we want to know what y is equal to when t is 4. All right. And we're going to round our answer to the nearest tenth. All right. So if we kind of go back to this over here, it says that this point right here, this is my initial amount. So my initial amount would be 250. And then my rate. Well, look at this. It has a 1.01. And notice that my growth factor is going to be 1 plus R. So really all I have to do to find out my rate is to simply do something like this. 1.01, subtract that 1 out. And I get that my rate is 0.01, but it asks for a percent. So what would that be? Well, using old school methods of moving the decimal, we would find that our growth rate is 1%. All right, this is the rate of growth, but our growth factor is the 1.01. Now it's just a matter of finding out what the answer is. So we can literally just use our calculator on this. It keeps it simple. We know that t is going to be 4 according to a problem, so let's just plug things in. 250, parentheses, 1.01, and we're going to raise that to the 4th power. And our calculator does all the heavy lifting for us. So this answer right here would be 260. And it's wanting me to round to the nearest tenth, so 260 point, what's that? 2. 260.2. And that's it, because that 5 tells that 1 to go up. All right, now let's look at the next one. So same concept. What is our A? Well, that's easy. It's this number right here. That's 14. What is my rate of growth? Well, I can look at it. I know I have a 1 here, so that's going to be 0.35 if I subtract it out, and we can just show that in calculator if you want to see it. And 0.35 written as a percent is 35%. And then my final answer after t is we just plug it in. 14 times 1.35, close that off, raised to the 4th power, and I get 46.5, and leave it like that. All right? So why don't you try the next ones on your own? 3 and 4. Try them on your own. Here are your answers for numbers 3 and 4. Pause the video if you need to. You know how to find me if you have questions. All right, let's look at number 5. It says credit card debt of $1,100 increases by 28% each year. Write and graph a function that represents this situation. So we're going to do this. We're going to claim our stuff. It already actually labels T down here for our X, so we know that this is going to be our time, and we know that this is going to be our money. Pretty easy. So let's just go ahead and label some things. We're going to say that this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Why not? All right, and then I'm going to leave this blank for the time being because, one, we don't know what things are going to be just yet. So let's go ahead and write a very simple equation of this. So it increases by 28% each year. That means that my rate, my R, is actually going to be 0.28. And the other thing is I have a debt of $1,100, so that's actually going to be my A. That is my initial amount. All right, now that I know that, it's just a matter of plugging things in. Y is equal to A plus 1, A times 1 plus R raised to the time. So let's just plug everything in. We're going to have 1,100 times 1.28 because 0.28 plus 1 is that, and then we're going to leave time. Now, I feel a little bit lazy. I'm going to use my calculator to help me out the rest of this. So I'm going to go to my y equals, just to kind of go back. If you go to y equals, we're going to plug in this equation that I just created. $1,100 times 1.28, close it off, and then I'm going to raise it to the x power. That's going to be my time. All right, I'm going to go to make sure my table is set correctly. I'm going to check out my table. So here are my numbers. At 1 year, this is how much after 1 year, this is how much debt I have incurred. So let's look and see what we have. Let's count by 500s maybe. Let's see if that one might do, because I'm looking at the numbers. We might be just running out of time. So we would have 500, 1,000, 15. We're just going to have to count by 1,000s on this because the number goes up. So the reason why I'm going to say 1,000 is just because by looking at the pattern, okay, it seems to be going pretty fast. So we'll go 1,000, 2,000, 3,000, 4, 5, 6, 7, 8, 9, and 10,000. All right, let's do our best to plug these in. So after 0 years, we have right here, somewhere about there would be our point. And then if we go a little farther, our 2 years, according to this, would be, 1 year would be about 1408, so it's about halfway. 2 years would be a little bit more, and we can't be exact on this just because we don't have a very detailed graph. 3 years would be 2,300, so somewhere around here. 4 years would be 2,900, so that would be about here, and I'm having to use my table here. 5 years would be a little almost here. 6 years would be 4,800, so right about here. 7 years would give me 6,100, so we're actually doing a huge jump on that one. 8 years would be a little under 8,000. And then 9 years would be a little above 10,000. All of a sudden it has a huge jump. So right about here, And if we were to do a 10th year, we're looking at way up here somewhere off of our graph. So this is the best that we can do. Now, if we wanted to see what this looked like on the calculator, we should be able to hit second graph and, oops, sorry, not second graph, but just graph. Let's see what it does. It's not working, so let's see. We need to, because it's not up there, we need to change our zoom. So if we go to zoom, let's go to what's called fit. Let's see, zoom fit. And hopefully this should show it to us. It's going to change our graph ever so slightly. Give it a moment. And here it goes, it's starting to go now. So it had to zoom out considerably in order to us to even see this exponential function. And we can trace it if we want, and we can see those exact numbers and see how it just kind of, as the years progress, it just literally starts to skyrocket. All right, so we get a basic idea of this. All right, now, number 6, going back to this particular problem, it says you deposit $675 in an account that earns 3.4% annual interest compounded twice a year. All right, so this is what I want to talk about. It's what we call compound interest. All right, so this was that last equation, and I'm going to try to put all this on screen for you. Pause the screen and write this stuff down because it's going to be very useful to you, especially what you see over here. But I'm going to walk you through it. Again, Y represents the final amount, and P is what we call the principal. This is the money that you start with, the initial amount. And then we have the annual interest rate, and again, this is going to be turned into a decimal. And then these two pieces are the new one, and I'll talk about that in just a moment. And then lastly, we have time. So let's go back and talk about what these N represents. This represents what we call compounding, times compounded. All right, so you think back to 7th grade when you were working with what we call something that was called simple interest rate. I equals PRT. You probably would remember that equation in some form or fashion. That right there is just calculating how much money you would have if all we did was give you a small chunk. Let me give you an example, and you don't have this in your notes, but I did want to show this to you. So if we were to say that I gave you $1,000 to invest at a 7% rate, after 1 year of plugging that into a bank, you would have $1,070. After 2 years, you would have $1,140. And what you probably should notice is that just after each year, you're gaining only $70 every year. That's simple interest rate. It's only how much you're getting per year. Compound interest is taking this money and then adding interest to this as well. So not only would you get $70 for the next year, but you would get a little bit more based upon the previous year. It just kind of adds up ever so slightly. But then it goes into even farther is how often it compounds. So let's kind of show you this example. So annually. Notice that these are the same number. After waiting for 1 year, you're going to have $1,070 if you compound annually. So every January, it just adds a little bit more. However, by the second year, you're going to have about $4 more than what you would if you were just following simple interest, because this is being compounded upon what you had before. And notice what ends up happening just by compounding annually once a year, where everything on simple interest is adding $70 a year. This is adding more than that per year. And if you were able to keep your money in the bank for a total of 30 years, this is the difference between the two. Simple interest, you would only have $3,100. However, by compounding annually, after 30 years, you would almost have double the amount. You would have double the amount, a little bit more. You would have $7,612 at your disposal just by compound interest. So if you notice in this thing, I gave you that N can be various things. We can compound annually, which we kind of showed, biannually, quarterly, monthly, and daily, and that's what N represents. So if I give you a problem that says you're going to compound quarterly, it means that your N has to be 4. So just to kind of show you the drastic change, I've kind of put this in here. So if we were to do the same concept, $1,000 to invest at a 7% interest rate, 1 year, simple interest and annually, going to be the same thing. But if you had compound interest twice a year, you're already $1 more than what you would be at regular interest. However, if we go even farther, if you were compounding every day, it's $2.50 more. Now that doesn't seem very much, especially after 1 year, but if you start noticing the numbers here, the numbers get pretty drastic. If we were to compare simple interest compared to compounding daily, after 30 years, you would have $5,000 more in your bank at your disposal just by compounding daily. This is the power of compound interest. All right, so I wanted to show you these numbers. So it's a little bit of here's kind of a question that I'm gonna let you think about. If you were to invest in a bank and put your money in the bank, would you like to have your money earning compound interest or simple interest? Now let's flip that question. What if you had to take a loan from the bank? Would you like your loan to be calculated where basically you have to pay that loan back? Would you like to have the bank calculate your loan payments based upon compound interest or simple interest? Think that one through, just a little fun thought. All right, so that's kind of the basis of what compound interest is. It's basically, it makes more money for you. Now, with all that said, let's just go ahead back to this question number 6. All right, and I'm going to write that equation to the side. My final amount is equal to my principal times 1 plus my rate over my times compounded time, all raised to the NT, which is my year times my numbers compounded. And T is always in years, by the way. Anyway, let's go through this. It says, write a function that represents this situation. So I'm going to use this and plug in everything that's important. I know that we're going to have Y is equal to my principal, which is $675. And we know that it's going to be 1 plus this interest. So if we have to change this into a decimal form, it's going to be 0.034. Divide by, and it says that it's compounding twice a year. So I'm going to actually divide by 2, close my parentheses off, and now I'm going to have to do NT power. So it's going to be 2 times T, because it doesn't tell me how many years I have right now. So that's a very simple function that we have written. Now it just tells me to find the balance after so many years. So it's that same equation again, and I'm going to rewrite it. This time I'm going to include my 2.5 in there. And now I'm going to show you how to do this in your calculator. When you are trying to find how much your final balance is going to be, or your final amount, the best thing for you to do is to remember PEMDAS, work inside out. So please excuse my dear Aunt Sally. So parentheses, so I have to work inside these parentheses first. So I've got to concentrate on just this. Now that I'm inside my parentheses, I need to follow the rest of PEMDAS. I'm going to have to divide first. So 0.034 divide by 2 gives me this number. I'm going to now add 1. All right, so I've done this piece in the parentheses. Now I need to go and do my exponents. So this has 2 times 2.5. So 2 times 2.5 is actually 5. So I'm going to raise this number to the 5th power, and it gives me this. And then lastly, I'm going to multiply it by the 675. So if I were to keep this amount of money in a bank, after 2.5 years, I would have $734, and we're going to round this to the nearest cent, 36 cents. All right. So again, when you're trying to do this equation, remember your rules of PEMDAS. Work from the inside out. All right. So that's it for this video, and I will see you in the next one. Bye-bye.